Hello everyone and welcome back to Teach Astronomy. My name is Victoria, but you can call me Vicky. And I'm adjusting my camera right now. There we go, that looks good. And welcome back to Teach Astronomy. As I said, my name is Victoria. Today is Monday, which means that we're doing another chapter of Dreams of Other Worlds. We're actually finishing up an old chapter that we didn't finish last time. The schedule's been a little weird lately because I have another job that's starting to conflict, but we're getting through it. We're going to get through this book. If you are new here, this book is called Dreams of Other Worlds. Like I said, it is by Chris Impey and Holly Henry, and it is the amazing story of unmanned space exploration. So every chapter is about a different unmanned space mission. So things like the Mars rovers, Voyager, Viking, stuff like that. What else did we talk about? Cassini, Stardust, Soho, Hipparcos, lots of stuff. So I think we are just going to jump right into it because like I said, that other job needs me there at noon. So I'm going to drink a little bit of water, and we are going to just hop right in. So last time we talked, we did the first half of the Spitzer chapter. So if you guys are following along with your own book or anything, I am on page 226, if that helps. Hopefully it will help. And it's the soft cover version. I don't know if there's a hard cover, but I don't have it. So let's just start this up. All right. The light of our sun. Human eyes, and all vertebrate eyes, are actually protrusions of the brain. Michael Sobel explains, quote, embryological studies show that the eyes begin to develop very early as two small buds on the neural tube that eventually becomes the brain, end quote. We often think of ourselves as the pinnacle of evolutionary adaptation, but the human eye is adapted to detect a very narrow slice of the overall electromagnetic spectrum. This is not at all accidental. Had our sun been a brown dwarf, emitting most of its light as infrared, our eyes would likely be adapted to infrared wavelengths. Some animals and insects, in fact, can see in wavelengths altogether invisible to us. Pit vipers have a sensory organ located near their eyes that allows them to detect infrared or thermal images of prey. Butterflies are thought to have a wide range of vision and can identify potential mating partners by ultraviolet markings on their wings. Bees, many types of fish, and some birds also see in ultraviolet light. Scientists have recently discovered that flowers and plants, when viewed in ultraviolet light, often display patterns invisible to us and color quite distinct from the color we see. By imaging flowers in ultraviolet light, scientists realize that the patterns revealed in ultraviolet apparently serve as landing strips, or markers useful in guiding insects to pollinating portions of the flower. At least 40 to 60 different types of eyes, with up to 10 distinct means of forming images, have independently evolved, from simple constructions like a patch of skin acting as a photoreceptor, to the compound eyes of flies and spiders, to the sophisticated eyes of the hawk or squid. Quote, the result is an enormous range of eye types using pinholes, lenses, mirrors, and scanning devices in various combinations to acquire information about the surrounding world, write Land and Nilsson. Not all eyes are paired and placed on the head. There are chitons with eyes spread over their dorsal shell, tube worms with eyes on their feeding tentacles, and clams with eyes on the mantle edge, end quote. Various cave-dwelling animals, because of a lack of light, have evolved without eyes. Some lizards, frogs, and fish, though they have complex eyes, also sport at the top or back of the head a third eye, or parietal eye, I think it's it, that at the least can indicate the presence or absence of light caused by the passing of a predator's shadow. Even such a rudimentary eye offers valuable survival information. Hello, ASMK. Welcome to the chat. If you guys are here, let me know. Thanks for coming by. Hope you've been doing well. Hope your weekend was good. At the other end of the spectrum of eye development are box jellyfish that have 24 eyes of 4 different types, 2 of which are extremely similar to human eyes. Existing for 600 to 700 million years, jellyfish have survived 5 mass extinctions, but they're often incorrectly characterized as not having a brain. Researchers recently found that neurons in jellies occur in neuronal centers distributed throughout their bodies, and that they purposefully navigate within their environment. Box jellyfish use the acute vision of their pseudo-human eyes to see under and above water in navigating to and from underwater mangroves in order to feed, as a story in the New York Times reports. Quote, "Not only are the eyes equipped with a cornea, lens, and retina, as human eyes are, but they are also suspended on stalks with heavy crystals on one end, a gyroscope-like arrangement that ensures the eyes are focused unerringly skyward. Every morning they must return to the roots or risk starvation. They rise toward the surface, and their upturned eyes scan the sky, until at last they spy the mangrove canopy." End quote. Beyond even these complex eyes are those of the cephalopods, like the octopus or squid, believed to be the most sophisticated eyes on the planet. Cephalopods focus their eyes with fine movements of the lens, unlike vertebrates, and they can automatically keep their pupils horizontal and even sense the polarization of light. That's the end of that section. Seeing in the dark. The largest and most densely populated habitat on Earth is the ocean realm. As Claire Nouvian observes, quote, "The deep sea, which has been immersed in total darkness since the dawn of time, forms the planet's largest habitat." End quote. Zoologists and oceanographers are far from documenting the welter of sea life. Quote, "Current estimates about the number of species yet to be discovered vary between 10 and 30 million, writes Nouvian. By comparison, the number of known species populating the planet today, whether terrestrial, aerial, or marine, is estimated at about 1.4 million. End quote. Downwelling light, whether sunlight or moonlight, in the upper reaches of the ocean's water column can reveal an animal's location or hideout. To avoid predators, marine animals largely forage for food at night, under cover of darkness. The result is that the ocean's water column is the size of the largest daily animal migration known, with marine animals migrating vertically as much as tens of meters to a kilometer. Harbor Branch Oceanographic Institute scientist Marsh Youngbluth explains, quote, "Each evening and morning, all the oceans and even the lakes of the world are theater to mass movements involving billions and billions of creatures swimming from deep waters to the surface and then back again to a colder, darker world. 60 years ago, when active sonar was first available, captains of fishing vessels thought that the bottom was rising under the boat. This phenomenon, called the vertical migration, is the largest synchronized animal movement on Earth. Like nomads in deserts, they move to and from the surface waters in search of an oasis. The first 100 meters of the sea, where the sunlight still penetrates. The photic zone, abounding with food. The signal that triggers and resets this ritual is the daily waning and waxing of sunlight. So travel frequently starts at dusk and ends at dawn." End quote. Although the deep sea is one place sunlight cannot reach, light and vision are no less critical there than for landlocked creatures. The spookfish, for instance, lives at 1,000 meters depth in cold, dark Pacific Ocean waters and has reflective telescopes for eyes. Spookfish weren't exactly the first astronomers, but unlike any other vertebrates, their eyes included crystal mirrors that focus light on the retina. And some marine animals have evolved the equivalent of wearing Polaroid sunglasses. They can see polarized light, which assists in their discerning jellyfish and other nearly transparent species moving through the water column. Deep below the coral reefs, ocean animals produce their own light to see and lure prey, signal distress, or otherwise communicate, attract a mate, repel and stun predators, and countershade themselves. Nouvian contends that bioluminescence is the most common mode of communication on the planet. Approximately 90% of all ocean animals produce or deploy bioluminescence in some capacity. Also referred to as cold body radiation, or cold light, nearly 98% of the energy used in generating this living light affords only a minimal release of heat, presumably to protect the luminescent organism from being detected by predators who sense infrared. Bioluminescence has evolved independently to some 40 to 50 times as a result of its clear survival advantages. While fireflies provide the most familiar example, a handful of land-based organisms luminesce, including fly larvae, as well as some earthworms, snails, mushrooms, and centipedes. In the ocean realm, bioluminescence is the rule rather than the exception. Ranking among the bioluminaries are bacteria, snails, krill, squid, eel, jellies, sponges, corals, clams, seaworms, green lantern sharks, megamouth sharks, and an array of fish. Inhabitants of midwater habitats luminesce at varying intensities to countershade themselves and blend in with downwelling light, so what? Sorry, I don't know what this... Let me try reading this sentence again. Inhabitants of midwater habitats luminesce at varying intensities to countershade themselves and blend in with downwelling light, so informative in the ecology of the water column. Lanternfish, of which there are at least 200 species, can illuminate photophores along the entire length of their bodies to provide countershade. Quote, photophores are often highly evolved structures, consisting not only of a light-generating cell, but also a reflector, lens, and color filter, explains Scripps Institute oceanographer Tony Koslow. Quote, most photophores emit light in the blue end of the spectrum to match the wavelength of downwelling light. End quote. Viperfish and deep-sea anglerfishes have attached to their bodies a kind of a fishing rod with a lighted lure that attracts sizable prey directly into their toothy mouths. Marine biologist Edith Whittler notes other deployments of bioluminescence in the ocean depths. Quote, there are many fishes, shrimps, and squids that use headlights to search for prey and to signal to mates. And as with some cars, some headlights can be rolled down and out of sight when they are not in use, a handy way of hiding that reflective surface and allowing the fish to better blend into the darkness. Most headlights in the ocean are blue, which is the color that travels furthest through seawater and the only color that most deep-sea animals can see. But there are some very interesting exceptions, like dragonfish with red headlights that are invisible to most other animals, but that the dragonfish can see and use like a sniper scope to sneak up on unsuspecting, unseen prey. End quote. Oh! Amira Siofra. Is that Amira Siofra? I think that's how you say it. Jellyfish, yes. Thank you for hosting us. Yeah, we are talking about jellyfish now. In a book about space. Amira Shifra. Oh, okay. Gotcha. Amira Shifra. Welcome to stream. We're talking about jellyfish in a part of a book about space travel, about Spitzer Space Telescope, and I do not know how we got here. The ocean is like space. That is partially how we got here. It's been interesting. Thank you so much for hosting us, and welcome to the stream. Deep-sea prawns and some squid emit bioluminescent fluids to startle predators and evade being eaten. Koslow reports, quote, some jellyfishes jettison bioluminescing tentacles before making their escape, much as a lizard may let go of its still writhing tail to occupy its predator while effecting its escape. End quote. Other jellyfish can spray their predators with a luminescent substance that makes the predator in turn visible to fish looking for a quick meal. Medical researchers are only beginning to realize what we might learn from deep-sea bioluminaries. Off Puget Sound in the Pacific Northwest live the Aquioria victoria jellyfish, from which green fluorescent protein, GFP, was first derived and used to generate other fluorescing marker proteins crucial in cancer and brain research, and invaluable to cell biology and genetic engineering. What zoologists discover about the variety of species deploying bioluminescence in the deep ocean can help astrobiologists anticipate the life forms that might illuminate the icy oceans of Europa, or alien seas on exoplanets orbiting other stars. To that end, Spitzer and other telescopes nightly scour the skies in search of other worlds. And that's the end of that section. The ocean is like space because it's a giant area of unexplored areas. Yeah. I think we have explored, and we probably know more about space than the ocean. It's definitely, there's definitely a lot going on down there that we have not fully explored, which is pretty cool. The final frontier is in our own oceans. All right. Forming new solar systems. The cold and dusty nebulae in which stars form are also places where planets form, and Spitzer has helped to tell their story. Newborn stars are embedded in a circumstellar disk of dust and grit coalescing around the star as a result of angular momentum conservation in the collapsing debris cloud. Just as an ice skater spins faster as they bring their arms to their chest, a diffuse cloud with slight rotation shrinks to a rapidly spinning compact disk. Protoplanetary disks, like those in the Orion Nebula, are heated by a central star, re-radiating all that energy in the infrared. Gas giant planets like Jupiter or Saturn form within the disk in as little as a few million years, the blink of a cosmic eye. The disk then dissipates and leaves behind a sparse gruel of debris made from dust particles that have been recycled through collisions of larger chunks of rock and evaporation. Spitzer is perfectly suited to studying debris disks because the cool material easily outshines the star in infrared radiation. By comparing disks at various stages of their development, the evolutionary history of how solar systems are born can be pieced together. And I have a figure for you guys. It's really just a picture, but it's very pretty. Here it is. So this isn't exactly what is shown in the book, but it's essentially the same thing. So this is an artist's concept of a young star in its dense disk of gas and dust. So light cannot escape from the interior of the disk, but infrared radiation emerges unaltered and reveals the process of planet formation. Within the disk, theory predicts that matter can accrete from dust grains into several thousand moon mass objects in just a few million years. And that is how a solar system is made, which is pretty cool. And that is exactly what Spitzer is looking for, because we talked about this last time, but Spitzer is a infrared telescope. So, yeah. Cool stuff. All right. Spitzer's data indicates that the extremely dense early phase of disk evolution lasts a couple of million years. The process begins as microscopic particles aggregate into larger particles the size of dust grains. Rocky planets like Earth and Mars form by accretion. As grit grows into boulders, then mountains, then planets. A process that takes 10 million years. Spectra show that the dust is mixed with gaseous organic molecules, including water, steam, carbon monoxide, carbon dioxide, and methane. Soot or pure carbon grains are an important ingredient of planets and carbon-based life forms. So it was with great excitement that astronomers announced the discovery, a few years ago, of Buckminster fullerenes, or buckyballs, in deep space. Buckyballs are spherical molecules made of 60 carbon atoms arranged in hexagons and pentagons like the panels of a soccer ball. The name alludes to Buckminster Fuller, who designed geodesic domes that look like these carbon molecules. Observations made with Spitzer have shown that buckyballs, or Buckminster fullerenes, are common in hydrogen-rich regions of space, such as gaseous nebula, where stars are born. Buckyballs are surprisingly robust and may be linked to the emergence of life by forming stable cages for concentrating other molecules, and so accelerating interaction rates and chemical complexity. Spitzer is well suited to diagnose the chemistry of planet formation, because molecules have most of their spectral transitions at infrared wavelengths. The spectra of dozens of planet-forming disks have revealed interesting anomalies. Hydrogen cyanide, HCN, which is a major repository of interstellar nitrogen, is rarer around stars less than half the sun's mass than around solar-type stars. This implies that planets around low-mass stars are nitrogen-poor. Since nitrogen is a key biological ingredient, this implies that life might be rare or fundamentally different on planets of low-mass stars. Spitzer has also shown that rocky silicate material in the space between stars is a more... Oh, sorry. A yawn surprised me. Spitzer has also shown that rocky silicate material in the space between stars is amorphous in form, while silicates in the debris disks associated with planet formation have the sharper spectral features associated with crystalline silicates. In the lab, amorphous silicates can only be converted into the crystalline forms by annealing at a temperature of 1,000 Kelvin, which allows the molecules to gently reorient themselves. In protoplanetary disks, annealing requires recurrent flaring of the star during the first million years of disk evolution. In these cool regions that can only be observed with an infrared telescope, we can observe the early steps along the path to planets and life. And that's the end of that section. Interesting stuff. We talked about exoplanets. We talk about exoplanets every once in a while, but we talked about exoplanets extensively one with a fellow they used to be part of Active Galactic, our student group, and they are now going to do their PhD in exoplanet studies, which was pretty cool. But yeah, we talk about some fun stuff here. I wonder, are there any, because we normally do news streams on Wednesdays, but sometimes we like to switch it up and do like one specific topic. And if there are ever any things that like you guys want us to specifically cover, let us know, because we'd be totally down to do that, or try to find like an expert that we can get on stream and talk to us about that. All right. You just enjoy the topics. Oh, I'm glad. Diagnosing distant worlds. The discovery of planets orbiting stars other than the Sun was one of the most dramatic events of 20th century science. Until 1995, our solar system was unique. Since then, an accelerating pace of discovery has confirmed more than 1,000 exoplanets, with 4,600 more good candidates. Many of these are Jupiter-mass planets, orbiting Sun-like stars within 100 light-years. But exoplanet detection limits are steadily approaching Earth mass, and systems with as many... Oh, I tried to fight through that one, and I couldn't do it. But exoplanet detection limits are steadily approaching Earth mass, and systems with as many as 7 planets have been discovered. The majority of these exoplanets were discovered by an indirect method, where the orbiting planet induces a reflex motion, or a wobble in the parent star, and the wobble is detected by a periodic Doppler shift in the spectrum of the star. Some of the early discoveries were hot Jupiters, or large planets on close orbits around their parent stars. But the Doppler detection method reveals nothing more than a planet's mass and orbital distance. Spitzer, by contrast, can observe exoplanets as they pass in front of or behind their star. This is an eclipse or a transit. Only the small fraction of systems where the orbital plane is lined up with our sightline can show eclipses. The detectors can gather infrared light from large exoplanets that orbit close to their star, and they are heated to at least 1,000 Kelvin, if the star is within 200 light-years of our Sun. As a planet traverses the face of its star, it blocks some of the starlight. There's a temporary dip in the infrared signal of the combined system due to the planet blocking a portion of the stellar disk. This eclipse allows the size of the planet to be measured. Then, when the planet passes behind the star, this is called a secondary eclipse, the infrared signal again dips because the planet's contribution is missing from the system's heat signal. The size of the drop is the amount of infrared emission coming from the planet. Spitzer's extended orbit allows continuous observations over an entire exoplanet orbit, and the telescope's ability to measure small changes of just 0.1% in brightness makes these observations possible. And we have a figure for that. So let's give it a look. Here it is. So like I said, again, these are kind of all, I wanted to get like full color images for these because everything in the book is black and white, and I couldn't find exactly the same thing, but this is generally the same thing. So this is just showing a distant exoplanet. It's an artist rendering, but an exoplanet is partially eclipsed by its parent star in this artist impression. And Spitzer uses observations like this to taste the atmosphere of an exoplanet by seeing which atoms or molecules are absorbed by the atmosphere. So yeah, like it said, with when the planet orbits passes in front of the star, we're able to see how large it is and, see how it changes the infrared radiation coming from the star. And then when it passes behind it, we can also measure some stuff because the planet does contribute to some of the star's infrared radiation because it is, existing near the star. And it has some infrared radiation, so we can learn a lot from that. All right. NASA's Kepler spacecraft, launched in March 2009, is also looking for transits caused by exoplanets by staring at a region in the Cygnus constellation. Kepler scientists want to determine whether Earth-like planets, small rocky worlds with long period orbits, are common. The exoplanet Kepler-22b, which is 2.4 times larger than Earth, was the first planet found by the telescope to orbit in the habitable zone of its sun-like star. As with the Milky Way project that used data from Spitzer's GLIMPSE survey, Zooniverse's Planet Hunters project invites volunteers to assist NASA in digging through Kepler's data. Kepler sends data on more than 150,000 stars to Earth at regular intervals, and volunteers for Planet Hunters survey the stars' light curves to identify possible transits. Quote, Planet Hunters is an online experiment that taps into the power of human pattern recognition, organizers explain on the website. So far, 2 likely planets have been detected by citizen scientists in the Kepler data. As has been the history of science from its earliest days, non-specialists are making serious contributions to Kepler's scientific outcomes. While Kepler can predict statistically the ubiquity of planets in our galaxy, it takes the sensitive instruments of an infrared telescope to characterize their composition. Spitzer's ability to diagnose the atmospheric composition of remote exoplanets was a big surprise. Observations have been made on more than 24 exoplanets, with dozens more expected during the ongoing WARM mission. Spitzer project scientist Michael Werner explains the telescope's contribution to this effort. Quote, because hot Jupiters are rich in gas, different wavelengths arise from different levels in the atmosphere of different chemical constituents. Spitzer data have allowed the determination of planetary temperatures and of constraints on chemical composition, including the identification of water vapor, atmospheric structure, and atmospheric dynamics. End quote. Though Spitzer's primary mission was to detect objects hidden by interstellar dust, characterizing exoplanets may become its greatest contribution. In 2007, scientists first measured weather on a planet beyond the solar system. The planet HD 189733b races around its parent star in just over 2 days. Temperatures across the planet range from 970 Kelvin to 1220 Kelvin, which means winds of 6,000 miles per hour must rage to keep the temperature variation that modest. By comparison, the Earth's jet stream sails along at only 200 miles per hour. The exoplanet Upsilon Andromeda B is even more extreme. Day-to-night temperature variations are 1,400 Celsius, that's 2,550 Fahrenheit, and 100 times larger than is typical on Earth. In the young, dynamic field of exoplanets, there have been many surprises, and theorists' expectations are often confounded. One hot Jupiter-like planet was found to have carbon monoxide, but almost no methane. This violates models of hot gas giants, where most of the carbon should be in the form of methane. Another 2 planets are shrouded by dry, dusty clouds unlike anything seen in our solar system. These planets show little of the expected water or stream, meaning that, if present, water might be hidden under the clouds in the form of a scalding ocean. End quote. Oh, no, not end quote. End section. All right. This isn't too long of a chapter, so we actually are probably going to end pretty early. Hi, Parzival. How you doing? Welcome to chat. I'm doing good. How are you doing? We've got a pretty quiet stream today. Just hanging out, reading some books, you know. Small group book club today. All right. On planets and dwarfs. Somewhere in the twilight between stars and planets lie objects called brown dwarfs. Below about 8% of the sun's mass, physical conditions will never allow the fusion of hydrogen into helium, as happens in the sun. There may be a flickering of energy from the fusion of hydrogen into deuterium, but lower mass objects don't have a sustainable source of energy. When they're young, brown dwarfs are easy to observe in the infrared because they generate a lot of heat during their gravitational collapse. As they age, they get cooler and fainter. For example, a puny star 10% of the mass of the sun would have a temperature of 3,000 Kelvin and a luminosity 1/10,000th that of the sun. By contrast, a brown dwarf 5% of the mass of the sun would be 3 times cooler and a further 100 times dimmer. It would take 1 million of these feeble objects to equal the light of the sun. Some astronomers consider Jupiter a failed star or a brown dwarf. Models indicate that brown dwarfs likely host moons like those of Jupiter and Saturn, worlds replete with weather systems, geysers, volcanoes, mountain ranges, and oceans, even if, as on Europa, the oceans are frozen over. Set on a moon orbiting a gas giant planet in the nearby Alpha Centauri star system, James Cameron's film, Avatar, mesmerized audiences with its rendering of Pandora orbiting a Jupiter-like world whose swirled and rippled clouds resemble those of Jupiter and its great red spot. Cameron's Pandora, one of Saturn's moons, also happens to be named Pandora, abounds in colorful flora and fauna evocative of Earth's ocean environments, like the giant Christmas tree worms that suddenly retract when touched, the seeds of the sacred tree that float with the pulses of a jellyfish, and the photophores that dot the plants, animals, insects, and human-like inhabitants of Cameron's adventure tale. That the Na'vi have blue skin seems no accident or random artistic choice. In ocean waters, blue light is least absorbed and can penetrate into the depths, so that most deep-sea animals see solely in blue light. With the announcement in October 2012 of an exoplanet with a similar mass to Earth detected in the Alpha Centauri triple star system, Cameron's fictional depiction seems even more plausible. In part, what captivated film audiences was the bioluminescence with which Cameron painted his Pandoran forests. Having explored and documented deep ocean fauna in the film Aliens of the Deep from 2005, Cameron is familiar with the myriad bioluminescent sea life and readily projects similar plants and animals onto his imaginary world. Draped with waterfalls alight with bioluminescence, Pandora's forests teem with glowing fireflies and whirling fan lizards. The forest floor is carpeted with illuminating moss, while its stream beds are lit with the equivalent of sea anemones. In effect, Cameron anticipates how life might be adapted on an exomoon of a gas giant planet or a brown dwarf star. On such worlds, we might expect to find luminous biota highlighted with photophores, as Cameron predicts, or species with eyes better adapted to night or low light conditions. Even as felines have dark adapted vision superior to humans, the Na'vi have feline features and navigate the nighttime forest with far better facility than the character Jake. Cameron's bioluminescent world may have been inspired by Jules Verne's 20,000 Leagues Under the Sea, in which the characters, strolling on the ocean floor, encounter bioluminescent jellyfish and note their phosphorescent glimmers. Yeah. Actually, nearly all jellies in the deep sea are luminescent. Verne's voyagers likewise chance upon corals, the tips of which glow. In stark contrast to the 19th century perception that the ocean floor was devoid of life, Verne imagined the seafloor abounding in bioluminescence. An engraved illustration for 20,000 Leagues, titled On the Ocean Floor, depicts a kelp forest with large corals, crustaceans, and a flotilla of giant jellyfish whose bodies and tentacles radiate light. Cameron's vision of bioluminescent organisms flourishing on a nearby exomoon is similarly prescient. And I'm going to show you guys a picture of that engraved illustration. Also, you're just stuck with inspiring jam. I look good today. Oh, thank you. I have my hair up. That's the only thing that's different. Water does help as well, yes. I've got good lighting today. I opened the blinds and we're finally getting light in that's not like directly streaming in and like doing getting like broken up by the blinds to make it look weird. So we're looking good today. The intellectual streams do tend to be smaller, yeah. But that's okay because it's really fun hanging out with you guys. Okay, so this is zoom in a little bit. There we go. This is the that engraving from 20,000 Leagues Under the Sea. So you can see they mentioned the jellyfish up here and the corals and stuff. There's some crabs and things down here. They're a little hard to see. It's not the highest quality image, but and then there are the explorers. So it's pretty cool. Have any of you guys read 20,000 Leagues Under the Sea? Because I have not, but I should. It sounds really cool. One of those classic sci-fis, you know. Under the sea. Yes. Yeah, all of this is underwater. It's supposed to be all under the sea. And yeah, there are some crustaceans and stuff down here. So, cool stuff. All right. Back on Earth, the first brown dwarf was discovered in 1995. Spitzer has contributed to this research by detecting some of the coolest and faintest examples known, including 18 in one small region of sky sifted from among a million sources detected. Despite their extreme faintness, Spitzer can detect the coolest brown dwarfs out to a distance of 100 light-years. The outer layers of these substellar objects are cool enough that they're rich in molecules. The composition of the gas, and so the appearance of narrow lines that acts as chemical fingerprints in the spectrum, changes as the brown dwarf evolves. Most of the 800 cataloged brown dwarfs have atmospheres with temperatures in the range of 1200 Celsius to 2000 Celsius. The next category, with temperatures from 1200 down to 250 Celsius, has strong methane absorption in their atmospheres. There's overlap, and often confusion, between planets and brown dwarfs, because some giant exoplanets are larger and hotter than some brown dwarfs. The very coolest category of the brown dwarf, and the endpoint of their evolution, has recently been discovered. NASA's Wide Field Infrared Survey, Explorer, WISE, which was launched in 2009, has finished a scan of the entire sky at infrared wavelengths. In 2011, astronomers reported 6 of the coolest stars ever found, one of which has a surface at no more than room temperature. The WISE data have the potential to reveal brown dwarfs closer than Proxima Centauri, the nearest star to our sun. You see 3 astronauts? Yeah, I think, going back to the image really quick. So the point is to make them, so the whole point of 20,000 Leagues Under the Sea, I think, is like, they're exploring the deep oceans and stuff, right? But it is supposed to feel like this like alien world, while also using like creatures that we're familiar with. So like jellyfish, but they're giant, and like crustaceans, but they like look a little bit stranger and stuff. So yeah, they're supposed to kind of look like a cross between like divers and like astronauts kind of thing. So it's pretty cool. Kirk Douglas was in the movie. Was he really? That's cool. I haven't watched the movie. I haven't read the book, but I gotta do that. But yeah, it sounds really cool. Especially because I didn't realize, but they mentioned in this in the last page or two, apparently it was a very uncommon belief that there was like anything on the bottom of the ocean. So it was very much a sci-fi concept at the time that like it would be this lush, and like granted I guess it's not like lush or like very lit up, but there's a lot of stuff living down there, so it's pretty cool. It is mysterious, yeah. All right. Another promising mission in the search for dwarf stars and transiting exoplanets is headed by Harvard astronomer David Charbonneau and was designed largely by Philip Nutzman, an astronomer at the University of California, Santa Cruz. The M-Earth project is focusing 8 small robotic telescopes on 2,000 M-dwarf stars. The project targets particularly M-dwarfs, as they are smaller than the Sun, and transiting planets would block out a greater portion of the star's light, making them easier to detect. Studying nearby transiting exoplanets could afford astronomers a better sense of whether Earth-like planets are common, and additionally allow astronomers to discriminate the chemistry of their atmospheres. Within 6 months of launching their project, the team detected their first transiting planet, a super-Earth named GJ1214b, in orbit around a star 13 parsecs from Earth. In 2010, the journal Nature reported that the atmosphere of GJ1214b was found to be comprised either of water vapor or of thick clouds or haze, as on Saturn's moon Titan. Infrared investigations are planned to determine which of these options exist on the planet. With resources like Zooniverse.org, in the coming decade, the public will likely contribute to the search for biomarkers, such as ozone or water vapor in the atmospheres of these other worlds. Awash as it is in newborn stars and exoplanets, the universe may be teeming with life. Perhaps in some far future, humans will have physical, robotic, or other means of virtual presence on a nearby exoplanet, or one of its moons that, similar to Cameron's Pandora, teems with bioluminescent life. Astronomer Carol Haswell cautions, quote, "If any of this is to happen, however, we need to use our collective ingenuity to understand and repair the effects that our industrial activity and our burgeoning population are having on our own planet." End quote. What we learn from exoplanets, Haswell suggests, might be invaluable in understanding Earth's climate evolution and ensuring our own survival and that of our companion species. In the meantime, NASA and the astronomical community welcomed the public's contribution to one of humankind's greatest adventures, locating possible habitable planets, and, in time, the signatures of life in some dark and overlooked corner of the vast and silent wastes of interstellar space. And that is the end of that chapter. We finished that really fast. Oh my god. But yeah, that's all we got on Spitzer. Took a very interesting like biology turn there. That was pretty interesting. What'd you send me, Parzival? What do you got here? Oh, it's some information about that exoplanet, that GJ1214b. Cool. Also known as Gliese 1214b. It's 42 light years from Earth, discovered in November of 2009. It is classified as a water world and is the only example of such a planet yet to be discovered. Ooh. Sounds like it's modeled after, what's it called? What was the world? It's not the planet. The real planet is not modeled after this, but they modeled the that one like water world planet in Interstellar after this one. That's pretty cool. What is the next chapter about? So the next chapter is going to be about Chandra, which is, let me pull up some information about Chandra. The Chandra X-ray Observatory. Let's check it out. Oh, well, that's not the right button. Hold on. There we go. Oh. There. Whoa. Why is everything off? Let me fix that. Oh, it looks a little better. Yeah. But this is the Chandra X-ray Observatory page on NASA. So we will be talking about Chandra. Oh, it's their 20th anniversary soon. That's very exciting. There it is. As it says here, Chandra's made profound discoveries and contributed invaluable information about the cosmos and the wondrous objects within it. It is a X-ray telescope, and yeah, we're gonna learn about it next week. Should be fun. And I think we're actually kind of getting towards the end of this book. Let me look. So we have Chandra, and then let's go back to the table of contents. We've got Chandra, we've got HST, WMAP, and then a conclusion about New Horizons. Well, it's called, the conclusion's called New Horizons, New Worlds. I'm assuming it's about New Horizons. So, because this was written before New Horizons arrived at Pluto, I believe. So, it's like four more chapters. And then after that, I think we might actually be switching up what we do here on Mondays, at least for a little bit. I wanted to try something new and possibly play a fun narrative game about space with you guys. So we will see. We have at least 4 more weeks of Bookstream, though. I'll probably do. We might have to split one more chapter. We might have to split HST, depending on what that day looks like for me. It's in like 2 weeks. But everything else should be done in like a week. So yeah, 4 or 5 more weeks, and then we'll have another chat with Professor Impey about the book and stuff, because I think you guys enjoyed that last time. You thought no one was here to support Vicky, then there you are. But yeah, so thank you guys all for hanging out. I think I am gonna end early because like I said, I do have to work my other job in about an hour. So I'm going to go get ready for that, as long as that's cool with you guys. But on Wednesday, we are going to be doing astronomy news stream with Michael. We're definitely going to be talking about stuff with the... Oh, it's Alan Shepard Day. Amazing. Well, we will be talking about Alan Shepard Day for sure. Thank you for that reminder. We'll talk about that. We'll talk about the new discoveries and like science done by Moxie on the Perseverance rover, which is really exciting. I don't know if you guys heard about that stuff, but they've been working with, checking out the Martian atmosphere, seeing if they can turn it into oxygen and stuff. And it is pretty cool what they have found so far. So we'll be talking about that, some other fun stuff, whatever you guys want to talk about as far as like news goes. And then on Friday, we're going to do some amateur astronomy. Not totally sure what the topic is yet, but if you guys have any ideas, please feel free to let us know either today or on Wednesday, or at our little Discord, if you're a part of the Discord. I think most of you here are part of the Discord already, so. Gaming by Professor Impey. I'm going to see if I can work it out, where it really honestly depends on when we get to that 1K. So what Parsifal's referencing is when we get to 1,000 followers, I want to do a special stream, and I have some special things in mind, some special, a special giveaway, another book giveaway for our subscribers, and then like another special thing for everyone who's a subscriber, so that'll be exciting. What else? Oh yeah, and we're just gonna have like a huge, big, extra long stream where we do a bunch of different stuff, and Matthew will be there, and Michael will be there, and Professor Impey will be there, and the question really is just when are we going to do it, and will we be able to set something up where Professor Impey could like play maybe some Kerbal or something. If we can make it happen, as far as like getting him to a computer that can play Kerbal, because his computer that he has in his office is not equipped to do that, then hopefully we will do something like that. But yeah, should be exciting. Cyberpunk 2077. Oh my god. Have him play that. That's I don't know, is it still super buggy? I haven't played it yet. My friend who I share a Steam library with, they have it, but have not tried it yet because of all the bugs and the T-posing, where they just, like, you start driving a car and then the character stands up outside of the car and just goes like this. It's very funny. Or GTA, oh my god. We'll probably stick to a more chill space game, at least for the first one. But yeah, we'll see. Well, thank you guys all for hanging out today and for being here. Like I said, it was a small stream. It was a quicker stream, but I really appreciate you guys hanging out. It's a nice time. And then, well, you were joking, but I still think that would be very, very funny. So if I can convince him one day, I think that would be an excellent stream. But yeah, thank you, Student McLeod. Thank you everyone for hanging out, and I'll see you next time. I'll see you on Wednesday.